otherwise, I can go on with the talk and present a point that we didn't touch, but maybe you can do it later. I see a question. No, hand raised.
Yes, please, Kaul, could you open? Okay, perfect.
Hi, my name is Vikas Kaul. I work for Medtronic in Minneapolis. I unfortunately missed your talk, so I was really looking forward to it, but I guess I'll catch the recording somehow. My question is perhaps more on the experimental side. While you've done fantastic work on the mathematical modeling front, are there any good, reliable experimental multi-physics benchmarks out there?
Let me say, I will say no, in the sense that multi-physics benchmarks are not established. There are several benchmarks for electrophysiology, and there are benchmarks for mechanics, but fully multi-physics, I will say no. Then, of course, there is the attempt sometimes to bring out some benchmark to compare the activities of different groups, but regarding multi-physics, I will say benchmark not. But it's true that what one can do is to try reproducing, at least for the fully multi-physics model, let me call it like this. One can do the following, excuse me, can do the following, can attempt to compare the results against those for real individuals. Then, of course, this is not trivial because developing benchmarks for a normal art, let's say, is different than comparing against data and information that is coming from a patient. And the patient has a non-normal art. So it's very difficult to use benchmarks to drive the integrated models for the normal art because of the lack of data even. Instead, if it is technically possible to develop models for patients, that is for non-normal art, because for those cases you typically tend to have data. It's about agreeing on a common set of data and situations that can be reproduced to compare against with. Let's say, in terms of electrophysiology, things are more advanced. There are known benchmarks, and something is starting from mechanics, and data for electrophysiology is coming along with the clinical procedures in abundance, and for example, for sampling electrical data during mapping in a ablation room and so on. But mechanically speaking, we have images, and for fluid dynamics indicator, we have the macroscopic ones, not detailed informations. Can be inferred by a Claude Doppler rather than by macroscopic indicators like pressure volume loops can be inferred in different manners, but detailed information not that much.
Right, that's at the whole heart level. I was wondering whether there was a subsystem level benchmark that could allow the entire community to test out each of the individual physics as well as the coupled physics.
For the what? Yes, let's say for electromechanics, excuse me, I lost my voice recently. For the couple physics, there are some benchmarks that are being defined for not for the art, even for pieces of material and surrogate models, geometric models for the art that are concerning electromechanics. Yes, in that case, there is something. I think the groups of Gernot-Planck, Dussel and Axel Lowe also they are very involved in this kind of benchmarking activity.
Thank you.
Okay, so any additional questions for Luca?
Well, if not, I can complement something on the talk that I gave formerly. So in the talk of Natalia Trainova, we have seen massive use of artificial intelligence and machine learning to, let's say, establish links among pathologies and outcomes of pathology, and also to drive interventions. While my talk was more focused on the mathematical and numerical models, so the deterministic work. Still, Natalia called for a synergistic approach among the two fields, and which actually there is, and we cannot neglect. And also, we use this approach in our project as well. One of the manner in which we use it is to speed up somehow the solution of the electromechanical model. It is empowering the electromechanical model by replacing a core model like the active force generation model with a simpler model, less complex, but still very meaningful, by means of machine learning. So this was what Natalia called for at the end of her talk, basically, to use the detail of model-based results and simulation, but at the same time use machine learning to speed up and to provide information faster. I have a couple of slides. If Stefano agrees, I can share them.
Yes, sure. We still have 7 minutes to give you some.
Just a few slides that I borrowed from Alfio's talk, former Alfio's talk. It is the following: how to combine physics-based models, that is models, with algorithms that are mainly data-driven. Okay. Then also this split data-driven and physics-based can be seen also from a different perspective. But let's start from this. So basically, let's assume to consider two separate worlds. One in which we just use physics-based models. We'll call it white box approach, in which we know the physics that is establishing links between and among data and output. So we have data on the left, then this is entering in our white box that is describing the phenomenon or the physical process that we are interested in. And then out of this, we have a solution. And associated with the solution, we have an output. So this is the conventional modeling approach. Then on the other side, we have this data-driven modeling. We can call it black box approach, in the sense that the link among data and the output is established by, let's say, transfer functions, mathematical tools that are not making evident or clear the physics that is behind this link, if there is any link, if there is any mathematical model that is behind the following. So, of course, the two words are apparently separated, and maybe conventionally they are being treated in a separate fashion, being seen and interpreted as two separate entities and let's say procedural approaches. But in reality, they can work in a more synergistic manner. Because, for example, even if you have a white box approach, you perfectly know the model, you still are lacking information. The data that you need to have to feed your model can be defective, can be of low quality, and could be missing at all. And then at the same point, on the other side, with a black box approach, it is a pity that you don't attempt to use information that you know about a physical process that you plan to model. Okay, so there is a third way, basically, and is what we can call the gray box approach. The gray box approach, which is establishing a link among data and outputs by combining information, even partial, about the physical process or the characteristic law, or even about the physical principles that are behind the process with something or constitutive relations that are deduced by and from data through machine learning algorithms. So, for example, you know the model, but you don't know let's imagine that is a mechanical model for the heart tissue, and you know the physical principles, balance of momentum, but then you don't know the characteristic law in that case. So you can imagine to use the machine learning tools to learn a relation among inputs and outputs at the level of the model, which can be relations among, I don't know, strains and stresses. And this, of course, is in need of data. Then I see another manner in which this gray box approach can be used is not only to learn the basics, let's say to learn something that is complementing the basic laws that you assume to know, but something that is eventually learning the whole model from data. So basically, you're replacing the model. The idea is the following: is that you replace the allegedly known model that is behind certain physics with a model that you surrogate from data. Okay, but at the same time, inside this, let's say, context, what you can do is to add constraints or other informations that you already know. So, for example, if you know that you have to establish a relation among data and quantities in the output, and I don't know, the physical process that is behind is blood flow dynamics in the chamber, well, you know that in that conditions the blood flow is incompressible. So you know something about the physical process, and you can complement information coming from machine learning world with constraints or basic principles that you can use to augment the merely based extrapolation of information coming from data. So there are, of course, different manners in which you can combine these two words, and also something that we did kind of successfully for developing our own active force generation model for the electromechanical context was based on the following. We know from experimental data relations among the values of the concentration of calcium in the cell, and we know the force that is generated by the cell in different conditions. But at the same time, we have physically based, very sophisticated excuse me, models that are providing the very same links. So one thing we can do is that we can train our reduced model based on artificial neural networks, not only using experimental data, but also using numerical results coming from physics-based models to complement and augment the training set data and also the testing set data. So this is the example that I precisely did before. So use a synergistic manner to use reduced order modeling and artificial neural networks inside the electromechanical model to maintain high the meaningfulness and significance of the model, but at the same time to reduce the complexity, the computational effort. Or my colleagues used it in a very efficient manner in relation with electrophysiology. So, for example, we used deep neural networks to build reduced order models for electrophysiology. That is to provide very rapidly numerical results and numerical solution of the electrophysiology field in the tissue by varying data, or better saying parameters. For example, these parameters can be the location of a scar in the tissue to see how the electric field is answering to this parameterized behavior, or by varying over time. So the time can be interpreted as a parameter itself. So of course, in this case, the model is the reduced model is even more complicated, because the idea here is not only to establish a link among data parameters or simplify the quantities of interest, but is to reproduce the whole computational field, the whole electrophysiological field. Then, as far as I know, just to make a further example of this, and then I stop because I jeopardized the whole coffee break. If I'm not wrong, there will be a talk later in room number 3 by Riccardo Tenderini. It will present a novel approach to build a reduced order model. Let me try to find it. To build a reduced order model that is working in a synergistic manner with the physics-based model to recover and to build the electrophysiological field with application to the atria. Right, Stefano?
To the ventricles.
To the ventricles.
Constructing the activation pattern of the ventricle.
We have several examples in which these synergistic approaches of data-driven models and models that are physics-based can help the field, not only to develop more efficient computational models, but at the same time to provide better, more qualified, and in a more efficient manner clinical answer to non-clinical problems.
Hey, thank you, Luca. So we have time just for quick questions. Then we will resume with the next talk. So, so if not, I would like to thank Luca also for this additional mini talk.